Good afternoon, all of you. Today,
Good afternoon, ma'am.
good afternoon. Today, I will be starting with the preliminaries required for the second course outcome of the course Kinematics of Machinery. So, the first course outcome pertain to concepts of mechanisms like links, pairs, degrees of freedom, inversion, indices of merit, and synthesis. And I think you also underwent some training on synthesis of planar mechanisms. So that pertains to course outcome one. Now the course outcome two is concerned with analysis of various mechanisms, analysis of the mechanisms that you synthesize as a part of mechanisms design. So the course outcome two runs like this, reads like this: analyze the motion characteristics of various links or points on various links of simple planar mechanisms. What we mean by that, this and all that we will be understanding in due course. So this course outcome corresponds to the second unit of our syllabus, the title of which is kinematic analysis, under which we'll be studying about displacement analysis, not very rigorously, but velocity analysis, acceleration analysis of simple mechanisms. There are graphical methods as well as analytical methods for carrying out kinematic analysis of mechanisms. Initially, we will be learning about graphical methods, and later on, if time permits, we'll go ahead with the analytical method. And of course, it is now possible to carry out kinematic analysis using computer programming as well as commercially available software, which we will try to at least introduce at some later point of time. Okay. So we'll be learning about the need for kinematic analysis, what exactly we mean by kinematic analysis, what we will be doing here, and what is the need for carrying out kinematic analysis of mechanisms. Then position on or displacement analysis. This not much of displacement analysis will be covered because actually going by the graphical method, the position analysis will be a very simple drawing of diagram. I will explain later on. And so we will be very rigorously carrying out velocity analysis and acceleration analysis of mechanisms. So initially we learned about mechanisms, the topology or definitions. I think now all of you are familiar with the definitions like what a link is, the types of links, what are the different types of pairs, kinematic, what we mean by kinematic chain, and when a chain becomes a mechanism, and how to calculate the degree of freedom of a mechanism for a planar case, what if it is a special mechanism, what inversions are, why we have the concept of inversions, what are the various inversions of the different types of chains like four bar chain, single slider chain, and double slider chain. Then probably you were introduced to the indices of merit in terms of transmission angle and mechanical advantage, toggle position, and so on. I suppose all of you are familiar with all these concepts. Moving ahead, probably you were introduced to synthesis of mechanisms, simple mechanisms, planar mechanisms. So there are different three major stages of synthesis. We start with what is called as type synthesis. Then we move on to number synthesis, and finally, our major task is to uh, carry out dimensional synthesis, where we decide on the length parameters or the lengths of various links of a linkage type of mechanism. So we can synthesize a mechanism for coordinating positions or for coordinating angles and or for coordinating say their derivatives like velocity and acceleration also, but of course I think we did not touch that. So the three major classification of dimensional synthesis are function synthesis, path generation, and motion generation. I'm sure you are all familiar with all this. Now, our task today at hand is analysis. Synthesis is creating something newly, and analysis is analyzing its performance, whatever you've created, analyzing the performance of whatever you've created is called as analysis. So, in our case, analysis of mechanisms, once you synthesize a mechanism for based on function generation, path generation, or motion generation type of problem, you need to analyze its performance by carrying out displacement analysis and then velocity and acceleration analysis. Uh, so suppose you synthesize a mechanism, or suppose there is a synthesis problem given to you. Every one of you, all 35 or 36 of you, will come out with different solutions. Each one will have his or her own solution for the same problem. But I need to find out which of the, suppose I have 35 mechanisms given by all every one of you to cater to some problem or to do some work out of the mechanism. Then but I need only one mechanism. I need to select the best out of the 35. So initially we have this set of indices of merit, like the transmission angle, mechanical advantage, like Grashofian, if it's a four-bar mechanism, Grashofian and non-Grashofian, and so on. So based on the indices of merit, you can eliminate some of the mechanisms or discard some of the mechanisms and choose a smaller set. But even among the smaller set, you will have to identify the best for which we need to carry out kinematic analysis in terms of displacement, velocity, and acceleration. What we mean by this is will be clear now. Why kinematic analysis? Okay. So we for any product to be designed, for example, suppose I need a mechanism like this, a hoisting mechanism. We need to design the various elements. So this is a hoisting mechanism where there is a motion involved. There is motion involved at different locations. So this will have to, this link will have to move. This link also will have to give, this is the input link. It will give motion to this link thereby, and then probably there is a drive here also, and hence this will be made to move. So motion is involved, and then there is a particular relative motion to be achieved between this link and this link. So you synthesize the mechanism for motion requirements. What do you mean by synthesis? Actually, synthesis is a part of a major task which is called as design. Can somebody tell me what we mean by design? What do we mean by design?
A structure that is made for a particular problem and a solution.
Okay. So design is, when we talk in common language, common parlance, design is creating something like fashion design. The other day itself, I might have told fashion design, interior design. So designing something is creating something. Okay, it's sort of creating something. But when it comes to mechanical engineering, it is, when I say design in the mechanical engineering context, or when it is mechanical design, we decide on the shape and size of a component which will go into a system. Okay, so this is what is meant by design. And when it comes to mechanisms design in particular, there are two major aspects. One is called as synthesis. Of course, you must be familiar with all this. Still, just for continuity's sake, I'm telling about this. The second aspect is the actual mechanical design. So these two major steps are there when it comes to mechanisms design, particularly design of linkage type of mechanisms. Okay. So synthesis is a task or is the activity wherein we decide on the lengths of various links, particularly of a linkage type of mechanism. Can somebody give me examples for linkage type of mechanisms? Examples for linkage type of mechanism.
4 bar mechanism.
Four bar, good. Four bar mechanism, slider crank mechanism, or single slider mechanism, they are all linkage type of mechanisms. Non-linkage type of mechanisms, non-linkage type of, other than linkage, okay? Gear mechanisms, cam type of cam and follower, belt chain drives,
Crack
they are
pinion.
rack and gear, generally gear type of okay, gear trains, which covers rack and pinion also, right? Worm wheel, every one of them. So all of these are special mechanisms. So mechanisms can be classified as linkage type of mechanisms and cam gears, cam follower, and so on. So when I say synthesis, the term is particularly applicable to linkage type of mechanisms where we decide on the lengths of various links only based on motion requirements. But if this say hoisting mechanism is to lift an engine which would be heavy, which would be having considerable mass, considerable mass, then these elements, these different links of the mechanism, they should be able to withstand the forces acting on the system. Here, the force is the major force is the weight of the engine that is being hoisted. So the cross section, this is length. The first is the length. When I say design, I mean the cross section. Deciding on the cross section is what is called as design when it comes to design of mechanisms, linkage type of mechanisms. So in order to design the cross section, we need to know the forces that act on the different links. So the different links will have to withstand the forces acting on each one of them, and we need to know the forces. Now let us see how they are all linked together. The major activity of design of mechanisms, how it is linked to kinematic synthesis, we'll now see. How uh, kinematic synthesis, where it comes, the need and all that, we'll now see. Okay. So now I suppose you understand that in synthesis of a mechanism, we take care of the motion like coordination between different links of a mechanism. For example, there may be a requirement that when the input link, say for example in a 4 bar mechanism, when the input link moves through say 30 degrees in the clockwise direction, the output link should move through 15 degrees in the clockwise direction. That could be a requirement. So that is a motion requirement, displacement requirement. So based on such requirements, you carry out the synthesis. So normally when you carry out synthesis, you must have learnt about Freudenstein's method of synthesis. Then the relative, yeah, inversion method, 4 bar function generation, and so on. So in all of those cases, we coordinate the input and the output motion in terms of displacement. Say angular displacement of the output link with some angular displacement of the input link. Or it could be the angular displacement of the input link of a 4 bar mechanism and some motion requirement of the coupler, as in the case of a path generation problem, right? But then we do not give uh, importance, or we do not give consideration to the velocity and acceleration of the various links of the mechanism, which also is important. So here we give more importance to displacement coordination, or what I mean to say is the displacement relationship between the input and the output link. But The mechanism has to work as a system where the different elements will have to move with different velocities and accelerations. So we need to carry out an analysis, which is called as a kinematics analysis. So in the design of mechanisms process, synthesis will be the first major task. After you synthesize a mechanism, you need to carry out an analysis. Some analysis you might have already carried out in terms of transmission and the mechanical advantage and toggle positions, limit positions, and so on. But they are all related to positions and displacement. Nowhere, I suppose, in your synthesis task, nowhere you analyzed about the velocities and the accelerations, which are very important towards, again, the design of a mechanism. So it is here that the kinematic analysis of mechanisms becomes important. So kinematic analysis of mechanisms, kinematic analysis is concerned with the displacement of the different links of the mechanism. Then the rate of change of displacement, which is a velocity. So velocity of different links of the mechanism. And again, another derivative of the displacement or the derivative of velocity, which is called as acceleration of the different links of the mechanism. When I say moving parts, I mean the different links of the mechanism. So the displacement could be linear displacement or angular displacement. For example, in all the links of a 4-bar mechanism, all the 3 links, the displacement will be, or at least the input and the output link, the displacement will be angular in nature, right? And in a slider crank mechanism, particularly the slider will have a linear displacement. And the coupler of a 4-bar mechanism that connects link number 2 and the input and output, or the connecting rod of a slider crank mechanism will have both, say, linear motion, translation, and rotation, which is called as combination motion or complex motion. We will see that later on again. Okay. And then when it comes to velocity, it could be linear velocity x dot dx by dt, rate of change of linear displacement respect to time, x dot. X dot is nothing but rate of change of displacement, x being the displacement. If it is linear, if it is angular or circular motion, it will be theta dot or omega, which is d theta by dt. This is linear velocity. What is this omega?
Angular velocity.
Angular velocity. And what will be the units? Theta by t. So in the denominator, you will have second. That's clear.
Degree per second.
Degree, or when we make
Radian.
omega, we make use of the term radian or unit radian.
Radian. Yes.
Radians per second. Okay? So the angular velocity will have units of radians per second. What about x dot? Linear velocity. What will be the units? Or
Meter per
unit?
second. Meter by second.
Meter per second, or if it is small in magnitude, millimeters per second. Is this clear? Okay. So the rate of change of velocity is acceleration, which will be represented as x double dot in case of linear motion and theta double dot in case of angular motion or circular motion. So x double dot is d of change of velocity, rate of change of velocity. If I represent x dot as v, so rate of change of velocity is x double dot, linear acceleration. So millimeter per. What will be the unit?
Millimeter per second.
Second square.
Second square, yes.
Velocity is already millimeters per second, is it not? So, or meters per second square, depending on the magnitude of this acceleration or velocity, whatever the quantity be, depending on the magnitude, you make use of meters per second or meter per second square or millimeter per second. whichever, representing in which way will be comfortable. Based on that, you will represent. Then theta double dot is the angular acceleration. We represent by means of the symbol alpha. Okay, and it is nothing but d omega by rate of change of angular acceleration. Rate of change of angular velocity is angular acceleration. So it will be d omega by dt. And what will be the units?
Radian per second square.
Radian per second square. Okay, so this in kinematic analysis, we'll be attempting to find out the displacement of links if it is required. Okay, and we'll be finding out the velocity of different links of the mechanism and the acceleration of the different links of the mechanism. Okay. So what is the need for finding out all this? Just a moment, I'll wipe off all this. So by carrying out a velocity analysis and then further acceleration analysis, you can find out the variation of acceleration over time. For example, if I have a 4-bar mechanism and I give a constant angular velocity of say 10 radians per second to the input link, the output link number 4 will not be having the same angular acceleration, the angular velocity. The angular velocity of the link number 4, omega 4, will keep changing over one cycle. So one cycle may correspond to 360 degrees of rotation of the input link if it is a crank. So from 0 to 360 degrees of rotation of the input crank, even if the velocity of that crank omega 2 is a constant, omega 4 will not be a constant. It will keep changing. Okay, and so you can find out the maximum magnitude of the acceleration and see if it is within reasonable limits. Secondly, so that is a part of the requirement of acceleration analysis. But then more than that, there is a very important need for acceleration of analysis of mechanisms, which is the design of the mechanism. So I told you the design of a mechanism is carried out in 2 stages. First is called as a synthesis, and second is the actual design of the various links of a mechanism. The joints and pairs also have to be designed. So here you decide on the length aspects. Here you design the cross-sectional details. What shape it should be. What do I mean by form? I mean shape. Circular, rectangular, I section, and so on. Okay, I shape and so on. So after synthesizing a mechanism, you need to carry out the kinematic analysis. Finally, in order to complete the design of the mechanism, I need to find out the shape and size of every link of the mechanism. So this link, I need to find out the shape. I also need to decide on the material out of which it is to be made. Okay, I need to find out the cross section of this, and here it is a cylinder. Okay, and here I need to select a cylinder of appropriate capacity, appropriate load capacity. Okay, so only then the design of the mechanism becomes complete. So when I say design of mechanism, I mean the design of various links and joints of the mechanism. This will be based on the constraint that the mechanism should not fail under operation. So what do I do here? I decide on the shape of the cross section and the size of the cross section. Okay. So in order to decide on the shape and size of a cross section, of course, I need to know the material. I need to select a material prior to coming out with the shape and size. Okay. Now, for example, consider this rod and imagine that it is subjected to a force like this, axial force. Okay. Now, can somebody tell me how I calculate the stress on this in this member? First of all, what are the various types of stresses?
Ma'am, tensile and compressive.
Okay, tensile and compressive together are called as what?
Longitudinal stress.
Normal, yes, longitudinal stress. Okay, tensile and compressive are due to longitudinal forces, and the stress induced is called as normal stress. We make use of the symbol. Kanna, yara answer பண்ணுங்க.
Sigma.
Sigma. Then, what is the second type of stress?
Shear stress.
Shear stress. We make use of the symbol tau.
Tau.
Yes. Now, in this case, in this example 1, what is the type of stress induced, normal or shear?
Normal, ma'am.
Normal.
Normal stress.
So how do I calculate the stress?
Load
Force.
by area.
Force divided by
Area.
axial stress, it's a longitudinal stress. Force divided by the area of cross section. How should the stress be? How should this be? Stress be? It should be less than. It should be less than the. Pardon me? Strength of the material, isn't it? It should be less than the strength of the material. Can you name one strength?
Ultimate strength.
Ultimate strength, yield strength.
Ultimate.
Yes, good. Ultimate strength is one type of strength. Yield strength is another strength. Usually for ductile materials, we make use of the yield strength. Okay, and then to be on the safer side, we apply what? We apply a
Factor of safety.
factor of safety. Factor of safety. Okay, so this is the induced stress. It is because of the force that comes on the link, and this is the area of cross section. So prior to designing the link, I will not be having the area of cross section, so I will not be able to find out the stress. The area of cross section is to be found out based on the stress induced, and by keeping maintaining the fact that or concept that the stress induced should be less than the allowable strength of the material, allowable stress of the material. Now, what does this depend on? This yield strength, what does it depend on? It depends on yield strength is a property of the material. Good. Yield strength is a material property. So, prior to designing a member, when I say designing this particular member, I mean finding out the area of cross section. So, if I want to find out the area of cross section, what are all the quantities that I need to know? I should know what?
Force.
I should know the force. I should also know the amount of stress that can be permitted on this component. Okay, which is dependent on my choice of
Material.
So before designing, I should know the forces, the maximum worst case force that comes on the member, and I should also know what material I propose to choose. Okay, so material, if you select a strong material whose strength is high, then you will have a compact arrangement, small cross-sectional area. If you select a material with poor strength, yield strength, then you will have to have a very bulky arrangement. Okay, and then when you select a material with high strength, the cost will be more. Then there will be other problems. There could be other problems like low toughness and so on. So you have to judiciously select a material. So once I select a material, I know the yield strength of the material being a standard material. So apart from that, I also should know the forces acting on the member. So if I know the force acting on the member, I can find out the area of cross section by dividing force by so the area of cross section will be the applied force, the force induced, I mean the force that comes on the member divided by the permissible stress. Okay. So now I suppose you understand that forces on various links of a mechanism have to be known if you need to design the mechanism. What do I mean by design? Deciding on the shape of the cross section and the size of the cross section. Okay. So that means you need to know the forces. Now, when it comes to forces, there are two types of forces which you might have learnt in your previous, say, mechanics classes. The forces could be static in nature or dynamic in nature. Static forces are forces that do not vary with time. Static forces are forces that come on stationary members. Further, they do not vary with time. When it comes to mechanisms, mechanisms are basically meant for what? Basically meant for what? Transmission of
Power.
Motion.
motion. Mechanisms are made for transmission of motion. Further, if they also transmit significant magnitude of forces or power, then it becomes a machine. Okay? Be it a mechanism or a machine, definitely motion is involved. Motion is involved. So whenever there is motion, of course, there will be velocity, there will be acceleration. So whenever a member is subjected to acceleration, uh, whenever a member accelerates or decelerates, it will be subjected to inertia force equal to mass multiplied by. How do you calculate inertia forces of bodies on bodies? Mass of the body multiplied by F equal to
Acceleration.
Mass into acceleration.
M. Yes, good. M into A. Mass into
Yeah.
acceleration. So if it is a linearly moving body, then this condition, this is a force acting on it. For a body undergoing circular motion, the counterpart will be inertia torque equal to I. M is the mass, I is the mass moment of inertia, A is a linear acceleration, and the counterpart in angular motion will be
Angular velocity.
angular acceleration. Angular acceleration. So mechanisms are dynamic systems. Different links will be having different velocities and accelerations at different instances of time, and hence will be experiencing inertia effects. They're together called as inertia effects. Inertia effects comprise inertia forces and inertia torque. So every element, every link of a mechanism will be subjected to inertia forces, inertia torques, varying magnitudes at different instants of time. So in order to find out, uh, so first of all, you need to know the forces, all the forces acting on a system, on a body to design the body. So if you need to know all the forces acting on the body, particularly for a mechanism, it's not enough if you find out the static forces. You also need to include dynamic forces when you analyze a mechanism for forces. So when I say dynamic forces, what are they? What are to be included? What are to be included? Inertia, forces, and what should I include? Apart from including the static forces, let me explain with this example. So when I say static forces, what is the force, major force that comes on this? It is the weight of the engine. So not. So this weight of the engine will cause this to experience some force. There will be a force acting here also. There will be a force moment force and bending moment, acting torsion moment also probably acting on this link. So all of these will be subjected to forces. Now when the weight is just held like this, when the engine is held like this, all of these will be subjected only to static forces. But when it starts moving, okay, different links, suppose different links have the movement, then all of them will be experiencing acceleration at times and deceleration at times. So apart from the static forces, we also have to include the inertia forces. When I say forces, I also mean torque, inertia torques. So then only the total forces, the net forces acting on a mechanism will be complete. So in order to analyze a mechanism, you need to consider dynamic forces. It's not enough if you consider static forces towards the design of the links of the mechanism. So when I say dynamic forces, it is static forces plus inertia forces, inertia force and torque. So inertia force and torque require a knowledge of what? Inertia forces require a knowledge of the acceleration of linear acceleration of different points on the links and the angular acceleration of rotary links. Okay. So all of these will have to be included in the dynamic forces to find out what? The stresses in various links. Once you know the total force acting on a link, then you can find out the stress. So in this case, the stress will be calculated as sigma equal to F by A. Here, stress is not available. Okay, when you are designing a member, force will be available based on the force analysis. And sigma allowable will be available based on the choice of your material. You will be finding out area. And then you will find out, you will decide on what the area should be, whether it should be rectangular, square section, or a circular section and so on, and then decide on the dimensions. Suppose this is a shaft. Imagine this is a shaft, then it will be subjected to torque. Okay, and it will experience shear stress. This of course might not be this might not have been taught as of now, I do not know. Then you need to find out so this is the torque. So where from I find out the torque acting on the shaft? Again, through dynamic force analysis, for which I need to know the accelerations of various links of the mechanism. Suppose this is something like this element here, okay? Then it will be subjected to a bending load. The bending stress will be calculated as, are you familiar with this equation? Bending equation? Vignesh? Are you able to hear? Janabal?
மேடம் கேக்குதுங்க மேடம்.
Okay, I can continue. Okay. So, யாரா நேம் சொல்லுங்கப்பா, நேம்ஸ் எல்லாம் மறந்து போச்சு. ஒரு பையன் நேம் சொல்லுங்க, பொண்ணு நேம், பையன் நேம்.
விக்ரம் ராஜுங்க.
நிக்கில் ராஜா.
விக்ரம் ராஜுங்க.
விக்ரம் ராஜு.
Yes, ma'am.
பதில் சொல்லுங்கண்ணா. One of you should volunteer.
Ma'am, I'm replying to all questions, ma'am. I'm giving others the chance. I'm always answering questions, ma'am.
பரவாயில்ல, இப்ப சொல்லு. இது வந்து எனக்கு இந்த ஈக்குவேஷன் ஃபெமிலியரா இல்லையா அதை மட்டும் சொல்லு. உன்னோட MOM
familiar, ma'am, but I forgot the terms, ma'am.
Okay, now in MOM, where are you in MOM? MOM ல போயிட்டு இருக்குல்ல. Are you familiar with this equation? Has this been taught?
Yes, ma'am. Yes, ma'am. Yes,
then composite bars?
Yes, ma'am.
அதெல்லாம் teach பண்ணிட்டாங்க. Then later on, after some time, probably you will get you get to know about this. You will be taught about this, and finally about the shaft shear stress in shaft. So what I mean to say is the two types of major types of stresses are normal stress and shear stress. Okay, different types of members will be subjected to normal stresses or shear stresses or combination of them also. And in order to design a member, be it a part of a mechanism or any other member, be it a static member, we need to know the forces acting on the member, okay, and the expressions for stresses, corresponding stresses. If it is axial stress, then the equation will be sigma equal to force by area. If it is bending, then again normal stress is induced, my by I. Of course, this you will be taught later on. If there is shear stress, depending on the type of, there are three different types of loads under which shear stress are induced, one of which is torque. T is the torque. So when a member is subjected to torque, shear stresses are induced, and many times many of the members are subjected to multiple loads. So both normal and shear stresses will act. Okay. So what I mean to say is, in order to design a member, you need to know what are the different types of forces that act on it, forces and moments also, bending moment and torsional moment. Okay. Apart from that, we should select a material. You should know the forces acting on the system. We should know the equations for the stresses. And then after choice of material, you will be able to find out the area of cross section. For example, here the stress is given by my by I. M is the bending moment, that is the force here, multiplied by this distance will give you the bending moment. F into L will be the bending moment. Y, of course, will be taught you later on. I is called as a moment of inertia of the cross section. So again, it depends on the cross-sectional dimensions. Okay. So you will be able to find out the stress only if you know the cross-sectional dimensions, or if you know the material and the allowable stress, then you will be able to find out the moment of inertia. That is, based on this, you will be able to decide on the cross-sectional details, the shape and the size. Okay. So now where does this kinematic analysis fit in? Why am I explaining all this? It is to tell you about where the kinematic analysis fits in the process of design and development of, or design of a mechanism. Suppose you are designing a mechanism from scratch. Suppose you are designing a mechanism from the beginning, then the first step will be spelling out your motion requirements. The second step will be to carry out a synthesis. The third step will be carrying out a kinematic analysis, where you carry out velocity analysis and acceleration analysis. Based on this, I'll find out, I will carry out a force analysis, and then finally, making use of the concepts of strength of materials or your mechanics of materials, I will be designing the cross-sectional details, that is shape and size for all the links of a mechanism. Okay. Now, do you understand the importance of acceleration analysis? This is particularly important for mechanisms because they are dynamic systems. Because motion is a very important, most important aspect of mechanisms. Okay. Shall I move on?
Yes, ma'am.
Okay. Okay. So initially, there are, of course, kinematic analysis can be carried out using the graphical approach or the analytical approach. A graphical approach is what we're going to start with. So initially, we will make a displacement analysis or a position analysis. Okay. And then we go ahead with the velocity analysis. So if the displacement analysis, the aim will be to find out the position, instantaneous position of various links of a mechanism. You can also find out the, based on positions at different instances of time, you can carry out a displacement analysis. The possible types of motions are, as I mentioned, any body in space can have a pure rotation type of motion, or it could be a pure translation, or it could be a complex motion. For example, if coming to an example from mechanisms, suppose you have a 4-bar mechanism, link number 2 and link number 4, which are pivoted here, connected to fixed frames here, they will have pure rotation, which could be a full rotation covering 360 degrees or a partial rotation oscillation. Okay, 2 and 4 will have pure rotation, which could be full or partial. Suppose you have a slider crank mechanism, then the slider will have what type of motion? What? A pure slider, this fourth link. Fourth link in the slider.
Linear motion.
Pure linear is pure translation. This will undergo pure translation. Here, link number 2 will have pure rotation. The crank will have pure rotation. Slider will have pure translation. Here, link number 2 will have pure rotation. 4 also will have pure rotation. Okay, but the nature of the velocity and all that will be different. Now, this link, which is called as a coupler in case of 4-bar mechanism, and connecting rod in the case of a slider crank mechanism. Okay, they are members which connect other members which are in motion. So both of these will have complex motion. This is a floating member. The coupler is a floating member. Connecting rod is a floating member. What I mean to say is, none of the joints, this joint and this joint, none of the joints on the coupler, none of the joints on the coupler is connected to a fixed frame. So this is called as a floating member. So is the connecting rod. Okay, the connecting rod, the joint here, it is not with a fixed link. Here also the joint is with a slider which is moving. Connecting rod also will be called as will come under the category of floating link. Okay, so such floating links will have what type of motion? Dhanabal, வேற name சொல்லுங்கப்பா.
Ma'am.
இன்னொரு நேம் சொல்லு, ஆட்டோமொபைல் ஒரு நேம் சொல்லுங்க. விக்னேஷ் நேம் சொல்லுங்கப்பா, ஸ்டூடெண்ட் நேம் சொல்லுங்க.
ஹரி பிரசாத் மேம்.
ஹரி பிரகாஷா, ஹரி பிரசாதா?
ஹரி பிரசாத்.
நான் நினைக்கிறேன் அடுத்த கிளாஸ்ல ஒரு பிரிண்ட் அவுட் எடுத்து வச்சுக்கோங்க. Okay, so floating links will have what type of motion? A complex motion. Yes, complex motion or a combination motion. What do I mean by that? It is a combination of rotation plus translation. Rotation, both rotation and translation will take place for the floating links. How do you identify a floating link? None of the joints on a floating link will be formed with a fixed link, fixed frame. Okay, okay. The position analysis, or rather the displacement analysis, finally will give you the relative displacement between links. So you can find out the limit positions, you can find out the toggle positions, the limit position, toggle position, and transmission angle, mechanical advantage, and so on. You can find out. Okay. Now moving on to kinematic, velocity analysis under kinematic analysis. This is based on this is for work volume requirements. You can find out what range of angle will the input link cover, what range of angle or linear area will the output angle cover, and all that will be evident or will be available from the displacement analysis. Whereas with motion, the velocity analysis and acceleration analysis uh, are related to the motion requirements. So velocity analysis, after you complete the velocity analysis, you will be having in your hand the velocities of all the points on the links. For example, if you again consider a 4-bar mechanism, okay, considering a 4-bar mechanism, after you carry out a velocity analysis of the 4-bar mechanism, so this input link, the angular velocity of the input link should be known in order to complete a velocity analysis for this mechanism. So I will be able to find out the angular velocity, instantaneous angular velocity of link number 3. I'll be able to find out the instantaneous angular velocity of link number 4. Okay. After you complete a velocity analysis, you will be able to, or you will be having the angular velocities of all links which undergo pure rotation or combination motion or complex motion. So after you complete velocity analysis, you will have in your hand the instantaneous angular velocities of all the links which undergo pure rotation or complex motion. Additionally, you will also be able to find out the velocity of any point on any of the links of the mechanism. For example, if I wish to know the velocity of this point, yes, it's possible. Name any point on this link or any other link for that matter, you will be able to find out the velocity of that point. So when it comes to velocities of points, it will be linear velocity. And when it comes to velocities of links, okay, it will be angular velocity, except the slider where you have a linear velocity. So V corresponds to linear velocity. Linear velocity pertains to points on links, points on various links like this, or it will also correspond to the slider. For a slider, you can find out linear velocity. For various points on any of the links of the mechanism, you can find out the linear velocity, meters per second or millimeters per second. And for all other links which undergo pure rotation like 2 and 4 here, or 3 which undergoes combination motion or complex motion, you can find out the angular velocity. So after carrying out velocity analysis, or the aim of velocity analysis is to find out angular velocity of all links which undergo pure rotation or complex motion, and linear velocity of slider if at all it's present in the mechanism. You can also find out the velocities of various points on the links. And similarly, when it comes to acceleration analysis, again the aim will be to find out, the aim of angular acceleration will be to find out the angular acceleration of what? Instantaneous angular acceleration of all the links which undergo pure rotation or complex motion. You can also find out the angular acceleration of sliders if at all they are present in the mechanism. If there is a slider in the mechanism, you will be able to find out the linear acceleration. I can also find out the linear acceleration of any point on the mechanism. Suppose you are interested in finding out the linear acceleration of this point x. I will be able to find out the linear acceleration. Okay. So what is velocity kinematic analysis? Kinematic analysis is the analysis of motion characteristics of a mechanism. It can be carried out after a synthesis process is over, or it can be carried out on any existing mechanism also. So kinematic analysis requires the mechanism to be already synthesized. Okay. So in kinematic analysis, we study about the relative motion characteristics of the various links of the mechanism. The two major tasks are velocity analysis and acceleration analysis. In velocity analysis, I attempt to find out the angular acceleration of all links which undergo pure rotation or complex motion, linear velocities of sliders, and linear velocities of any points on the. So that's what I mean by this outcome. Please read the outcome. It says velocity of all points or links. Okay, all points on any of the links. When it comes to links like this, it is angular velocity. Then, when it is acceleration analysis, the aim is to find out the instantaneous angular acceleration of all the links that undergo pure rotation or complex motion, and the linear velocity of sliders if they are present, and the linear acceleration of sliders, and linear acceleration of any point on the mechanism. So these are what is possible with the kinematic analysis. So by now you should know what we mean by kinematic analysis. Okay, what is the need for kinematic analysis? What is the outcome of each stage of kinematic analysis? Like displacement, position or displacement analysis, what is the outcome? Velocity analysis, what is the outcome? Acceleration analysis, what is the outcome? Okay. Now, this displacement analysis or position analysis rather, the results of position analysis will form the input for velocity analysis, and the results of velocity analysis will form the input for acceleration analysis. What I mean to say is, in order to complete an acceleration analysis, the mechanism should have been synthesized already, or it could also be a mechanism which is already in use in some company or industry. So first step is to carry out a position analysis. We need to carry out a position analysis. Then this forms, based on the position analysis, we carry out velocity analysis. After we complete the velocity analysis, only acceleration analysis will be possible, because the results that you get of velocity analysis will form the input for acceleration analysis. So you should also know where kinematic analysis fits in or stands in the process of development of a mechanism or design of a mechanism. What is the need for velocity analysis? What is the need for acceleration analysis? Okay. When I say need for acceleration analysis, there are two aspects. One is to find out the maximum values of acceleration of the different links, so as to see if they are within finite limits, achievable limits. The second is that the acceleration results of acceleration analysis form the input for dynamic force analysis. So these are the major needs. Okay. So I think I'll have to stop here, because this needs some time. Or Dhanabal, can I continue for some time, 5 minutes?
Okay, ma'am.
Okay. So that's about it. Okay. So with that in mind, let us see what position means, velocity means, and so on, how to go about with the analysis. So displacement analysis. First and before that, before displacement analysis, we need to know what we mean by position. So let us initially consider a point. The position of a point, we know what we mean by the position of a point. If you have a point, normally what we do is, in order to specify the position of point, we adopt a coordinate system, a planar or a spatial coordinate system like this, and we with the origin, I mean we relate this point P, its distance from the origin along the x-axis along the y direction, that we specify as the position of a point in plane. Okay. Now the same thing when it comes to analysis, we make use of what is called as the position vector. Okay. So imagine a point A here. This is a point A. Okay. And let us have a coordinate system adopt right-handed coordinate system adopted like this, a planar, okay, in the plane, because most of the analysis that we'll be carrying out will pertain to planar mechanisms. So let this be the x-axis and y-axis. This be the origin. Okay. Now, in order to specify the position of point A, we represent it as a vector because, for example, the concept of vectors to represent positions, it will be useful when you make use of the uh, analytical methods. Okay. So this is the point A. The vector OA represents the position vector of point A, which is represented as RA. RA is a position vector of point A, which is OA, by adopting a global coordinate system. So the x component being Rx and the y component being Ry. Now, in mechanisms, the orientations of links will be keeping on changing. So it is more useful to adopt a local coordinate system. Like what I mean is, suppose you have a mechanism like this or a robo mechanism, you can attach a global coordinate system to the fixed frame. And in order to analyze some points on this, it's preferred to have a local coordinate system like this. You can represent the position of point P here in terms of the local coordinate system, this new coordinate system x1, y1. And then x1, there could be a relationship established between x1, y1, the new local coordinate system, and the global coordinate system, capital XY. So by representing the point P in the local coordinate system x1, y1, and by establishing a relationship between the local coordinate system x1, y1 and the global coordinate system xy, you can establish the global coordinates of point P. So it is very useful when it comes to analytical method. So it is we are just giving an introduction now. So immediately we will not be making use of all this. Okay. So the same point A, initially we represented as Rx and Ry in terms of the global coordinate system xy. Okay. Then by adopting a new coordinate system, by rotating the original coordinate system through an angle of delta, you get a new coordinate system x, y. The point is not has not moved. Now, with reference to a new coordinate system, the position of A will be Rx, small x, and Ry. You can always establish the relationship between Rx and Ry. Isn't it? Like you can represent this RA square can be represented as Rx square and Ry square. Is it not? Or you can also represent like what I mean to say is Rx or capital X can be written as RA cos phi plus delta. Is it not? Rx will be RA cos phi plus delta, or Y will be RA sin phi plus delta. This RA can be written as Ra cos phi cos delta minus sin phi sin delta. Is it not? But what is Ra Ra cos phi? What is Ra cos phi from here? It is Rx. Small Rx is Ra cos phi. So not so this can be expanded. Ra cos phi cos delta can be written as R small x cos delta. So Rx can be written as capital X can be written as Rx cos delta minus Rx sin delta. So you can establish the relationship between the coordinates of the global coordinate system, original coordinate system, and the coordinates of the local coordinate system. So this will come in handy when you analyze mechanisms for position and velocity acceleration using the analytical method. So this is the position vector representing a point in space or in a plane with the help of a position vector. Then change of position causes displacement or is called as displacement. So the change of position, displacement of a point is a change in the position and can be defined as a straight line distance between the initial and final positions of a point which has moved in the reference frame. For example, consider this point A. So initially it is here and then it takes a path and reaches this point. Now, irrespective of the path traversed, when we talk of a displacement, it is the initial position and the final position only that matter. The point from A to B, the movement from A to B could have happened like this, So irrespective of the path adopted, when I say displacement, it is the distance, shortest distance or the linear distance between, straight line distance between the initial position and the final position. Okay. So representing that as vectors, so this is the initial position and this is the coordinate axis system. Ra is the initial position vector of point A. Mind that we are talking only about a point as of now. Now point A has moved to this location B and the final position vector of point A is RB. It is the same point that has gone to location B. Okay. Now the displacement, how to get at the displacement? The displacement is obtained by subtracting the final position minus initial position, isn't it? Will give you the displacement. So the displacement vector is represented as R. Final position to initial position is RB minus RA. So the displacement is defined as the distance between the final position and the initial position. And it is written as RBA. The final position is RB and the initial position is RA. So this is called as a displacement vector. Now if you want to represent this graphically, in order to find out the displacement vector RBA graphically, this is analytical. Of course, they are all vectors. You cannot straight away do algebraic subtraction. Suppose this is 100, this is 20. You cannot do this as 100 minus 20 because direction also is associated. They should all be carried out with vector manipulation, vector addition, vector subtraction, and so on, because the direction also is associated with it. Now, to represent this graphically, subtracting RA vector from RB vector to get at the displacement vector, we start with an origin and represent the position vector RB to scale. Start with the origin, position vector RB to scale. To scale means, what do I mean by scale? If this is say 48 degrees and suppose this is 100 millimeters, the position vector, I have to draw this to 100 and at the specified angle 48 degrees. That is what I mean by drawing to scale. Okay, so start with an origin O, then draw a vector to represent RB to scale. So 100 millimeters long and at an angle of 48 from the say horizontal. So position vector of B is drawn. Now to subtract, to get at the this vector, that is the displacement vector, you need to add to it minus RA. So now RA is like this, RA is like this, minus RA will be just exactly opposite to that. So to the end of RB, I need to draw minus RA like this. Again, you need to maintain, actually in your this diagram, RA is like this, but we need to go in the negative direction, and suppose this is 56, the position vector, the location is 56 from the origin. This has to be drawn to a length of 56 and at the specified angle. Okay, so this gives you RA. This is actually minus of RA. Now this side, this closing side gives you RB minus RA. This gives you the position vector, or rather the displacement vector, RB minus RA. So this is how you have to carry out vector addition or vector subtraction. I just go through this once again. If it's not clear, as we proceed further in the next slides, probably you will be able to understand better. Okay. So this is how you find out the displacement vector by means of the graphical method. So again, the displacements, I told you the motion can be, displacements can be of three types. Translation, pure translation, where all the points on the body have the same displacement like what you have here. Suppose this is a body. Earlier we talked about a point moving from location A to location B. Now we are considering a link AB or a body AB, initially like this. And so a body moving from here to here in every point on the link, okay, translating through the same amount or through the same displacement is called as pure translation. Okay, the same body, location being the same, suppose it is rotating like this, with this is the origin, with this is the center of rotation, A is the center of rotation, it is called as rotation, where different points in the body undergo different displacements, and thus there is a displacement difference between. So for example, this point A does not undergo any displacement at all, the displacement is 0. Point B has gone through to B dash, moving through such a large distance, and all the points in between will be moving through different displacements like this. So in rotation, different points in the body undergo different displacements, and thus there is a displacement difference between 2 points, any 2 points chosen on the body. Complex motion is the sum of translation and rotation like this. So this body has translated like this from here to here, and then it has rotated. So from the initial position of AB, the body comes to a position at A dash, B double dash, from here to here by undergoing a combination motion or a complex motion, which could be split into a translation like this and then a rotation like this. Okay, so with that, we will stop today. Tomorrow we will continue with our discussion on kinematic analysis. Thank you all.
Thank you.
Thank you.